In the world of automation, precision is paramount. Whether it's maintaining a steady temperature in an industrial furnace or guiding a robotic arm, accurate control is essential. This is where PID control comes in. PID stands for Proportional Integral Derivative, a widely used control loop feedback mechanism. PID controllers are the unsung heroes in countless applications, from simple thermostats to complex industrial systems. They work by continuously monitoring a process variable, PV, and comparing it to a desired set point, SP. Based on this comparison, the controller adjusts its output to minimize the error and keep the PV as close to the SP as possible. Imagine a self-driving car navigating a highway, constantly adjusting the steering angle based on the car's position relative to the lane markings. In essence, PID control is all about making real-time adjustments to achieve the desired outcome. Understanding PID control is crucial for anyone in automation, unlocking a world of possibilities in designing and optimizing systems. To master PID control, we need to break down its three core components: proportional, integral, and derivative. Each component plays a distinct role in minimizing error and achieving optimal control. Proportional, P control adjusts the output in proportion to the current error. A larger error results in a larger output adjustment. While effective, it can lead to a steady-state error where the system never quite reaches the set point. Integral, I, control addresses this by considering the accumulated error over time. It integrates the error signal, adding a corrective factor to the output based on the error's history. This helps to eliminate steady-state errors and ensures the system settles precisely at the set point. Derivative D control focuses on the future, calculating the rate of change of the error and taking preemptive action. This is useful in systems with inertia or lag, where sudden changes can lead to overshoot or oscillations. Think of the PID controller as a skilled driver. The proportional component is like steering the car based on its current position. The integral component adjusts for any drift or pull on the road. The derivative component anticipates upcoming curves and adjusts the steering accordingly. Now that we've dissected the components of PID control, let's delve into why calibration is paramount. Calibration fine-tunes the PID parameters, proportional gain, integral gain, and derivative gain to achieve the desired control performance. Without proper calibration, even a well-designed PID controller can behave erratically, leading to instability and inaccurate control. Calibration is essential because every system is unique. Factors such as system dynamics, inertia, and time constants influence the ideal calibration settings. A well-calibrated PID controller ensures the system responds quickly to disturbances, settles at the set point with minimal overshoot, and remains stable. In the following sections, we'll embark on a step-by-step journey through the calibration process. Before adjusting PID parameters, it's crucial to lay a solid foundation for successful calibration. This involves understanding the system and gathering the necessary tools. System identification. Gain a thorough understanding of the system's dynamics, response time, and any dead time or lag. Data acquisition. Monitor the process variable, PV, and the controller output using sensors, data loggers, or software interfaces. Tuning environment. Calibrate the PID controller in an environment that closely resembles actual operating conditions. Safety first. Implement appropriate safety measures before making changes to a live system. This might involve using a backup controller or limiting the range of output adjustments. By properly preparing, we can ensure the calibration process is both effective and safe. In the next section, we'll begin our calibration journey by focusing on the proportional gain. Let's get started. With our system prepped, we begin the calibration process by focusing on the proportional gain, or KP. This parameter dictates how aggressively the controller responds to errors. A higher KP value results in a faster response, but can lead to overshoot and instability. Start with the integral and derivative gains set to 0 to isolate the effect of the proportional gain. Gradually increase the KP value in small increments while monitoring the system's response. Observe how quickly the process variable, PV, approaches the set point and whether any overshoot or oscillations occur. The goal is to find a KP value that provides a fast response without excessive overshoot. Document observations such as rise time, settling time, and overshoot. This documentation will be invaluable as we fine-tune the other PID gains. Once we've established a reasonable baseline with the proportional gain, we can move on to fine-tuning the integral action. With the proportional gain providing basic control, we introduce integral action to eliminate steady-state errors. The integral gain, or KI, determines how aggressively the controller compensates for accumulated errors. Start with a small KI value and gradually increase it while observing the system's response. The integral term should help eliminate any remaining offset between the PV and the set point. Finding the optimal KI value is a balancing act. A higher key value will eliminate steady-state errors more quickly, but can also lead to increased overshoot and oscillations. Continue to adjust the KI value in small increments, observing the system's response until the desired performance is achieved. The goal is to balance eliminating steady-state errors and maintaining stability. With the proportional and integral gains set, we add derivative control to enhance responsiveness and stability. The derivative gain, or KD, influences how the controller reacts to the rate of change of the error. Start with a small KD value and gradually increase it while observing the system's behavior. The derivative term should help dampen oscillations and improve the system's response to sudden disturbances. One primary benefit of derivative control is its ability to reduce overshoot. By anticipating future errors, the derivative term can apply corrective action before overshoot becomes excessive. In systems with inertia or lag, the derivative term can significantly enhance stability. Finding the optimal KD value involves trial and error. Continue to adjust the KD value in small increments, observing the system's response until the desired level of responsiveness and stability is achieved. Note that derivative control can be sensitive to noise, so use a low-pass filter if necessary. While PID control is powerful, several common pitfalls can hinder its effectiveness. Overtuning the PID controller is a common mistake, leading to excessive overshoot, oscillations, and instability. Adjust the gains gradually and observe the system's response carefully. Every system has unique dynamics that must be considered during calibration. Failing to account for factors such as dead time, lag, and inertia can lead to poor control performance. Using an inappropriate tuning method for the specific system can result in suboptimal control. Noise in the system can interfere with the PID controller's ability to accurately measure the error signal. Use filtering techniques and ensure proper grounding and shielding to mitigate noise issues. Proper documentation is crucial throughout the calibration process. Record the initial PID settings, adjustments made, and the system's response to each adjustment. This documentation can be invaluable for troubleshooting and future optimization. By avoiding these common pitfalls, we can ensure our PID controllers operate effectively and reliably. Once we've successfully calibrated our PID controller, maintaining optimal control requires ongoing monitoring and occasional adjustments. Systems can change over time due to wear and tear, environmental factors, or changes in operating conditions. These changes can affect the system's dynamics and require adjustments to the PID parameters. Continuously monitor the system's performance and look for signs of degradation, such as increased overshoot or steady-state errors. For systems that experience frequent changes, consider implementing adaptive tuning techniques. These techniques automatically adjust the PID parameters based on the system's behavior. Periodically, review the PID controller's performance and make necessary adjustments. By adopting a proactive approach to maintenance, we can ensure our PID controllers continue to operate at peak performance. Mastering PID control requires a deep understanding of the principles, careful observation, and a willingness to experiment and refine. By breaking down the PID algorithm into its core components, understanding the importance of calibration, and following a systematic approach to tuning, we can unlock the full potential of this powerful control technique. From simple thermostats to complex industrial processes, PID control plays a vital role in countless applications. Embrace the iterative nature of PID tuning. Continuously seek opportunities to learn and improve, and never underestimate the power of careful observation and experimentation. By doing so, you can become a true PID control expert, capable of designing and optimizing systems that meet the most demanding requirements. The journey to mastery is ongoing, but with dedication, you can achieve precision and efficiency in your control systems.